So section 5.6, that's the final section, chapter 5. So we're going to do the test next week, review on Monday. So we're just dealing with exponential logarithmic models, so basically the word problems. And it all relates to our PERT formula. This is really the exponential growth model. So for the positive rate, we assume that r is greater than 0. This whole thing will eventually going to grow to infinity, so things are growing exponentially. So again, it's the same formula we used for the interests. Now your book is going to relabel everything here. Your book will call this formula probably n of t equals n naught e to the kt, where again, n of t is the amount or a number at time t, and naught is the initial amount, k is the rate. But in essence, that's the PERT formula, only relabeled differently. So this would be, so n naught, that's the initial amount, population, depending on what we're dealing with. K is the rate, and k is positive. So if you see a function with a positive exponent, it will grow. Okay. So since we already know how to operate with the PERT formula, we've done problems with that, and we solved equations, we should not have a whole lot of issues doing the word problems that are presented in this section. You just need to know one formula. That's it. That's the PERT formula, and you already know the PERT formula. They just relabel it for whatever reason. So I have some problems here. It's a bunny little problem. It's a fun bunny problem. Whatever you want to call it. It's from the previous class, so I didn't delete those. Yeah. So population of rabbits has an exponential growth rate of 11.7% daily. Okay. So part A is asking us to set up the exponential growth model, provided that we start with 100 rabbits. So then the answer is pretty straightforward. We have all the information that we need. N of t equals 100. That's the initial population. E to the power 0.117 t. So that's it. That's the model. You just have to plug in all the given information. Now when I grab this function, I'll get my regular exponential function. It will have the y-intercept at 100 and so forth and so forth. So if I plug this into, that's a different one. If I plug this function into foo plot, for example, I don't see anything, but if I go back, where's my little function? Okay, yeah, I have an extra symbol here. Here we go. So it's still an exponential function, has the intercept at 100, so basically you get a lot of rabbits very, very fast, right? So the next question is asking us, what will the population be after 7 days? So they give us the value for t, so all I have to do is to compute n of 7. Well, that's pretty straightforward. I just have to plug it in the calculator, and it'll just give me the answer straight up. So that's 0.117 times 7 equals whatever that is, raise e, okay, let's go back, raise e to that power, and then times it by 100, so 226 or 227 rabbits just after 7 days. depending what your philosophy on rounding. Do you just round up with 0.8, or 0.8 is just not a full rabbit, so it's technically 226 rabbits. So maybe your rules of rounding don't apply to actual beings. So for the 14, for 2 weeks, you just have to make sure you're in the same units of measure. So it's 14 days since t is measured in days. So some other number. We should be able to compute that pretty easily. So 0.117 times 14 equals whatever that is, raise e to that power times 100. So 514 rabbits. How's that? That pretty straightforward? There's no equations, no nothing. You just set things up. You just compute them. But the question, that's the interesting one. Find the doubling time, meaning how long does it take for the population to double? So we start with 100 rabbits. How long will it take to get to 200 rabbits? And we've answered a question like that with money. How long it takes for investment to double? Remember that on that little worksheet? There were 2 questions. One gave you the initial amount, was $10,000. You want to see how long it takes to turn to $20,000. On another one, I did not tell you the initial amount, but it doesn't matter. Basically, $1 has to turn into $2. Same thing with the bunnies. Yeah, we do know the initial amount of 100, but it doesn't matter. It takes the same amount of time for 100 bunnies to turn into 200 bunnies than it takes 17 bunnies to turn into 34 bunnies. The doubling time will be a constant for this problem. But the way we'll set it up, if we start with 100 bunnies, we want 100 to turn into 200. But again, it doesn't matter what you start with. The other side is double of that. So I can actually label it as n naught and 2 times n naught. So initial population, double that. Because every time you divide by the initial amount, one side of the equation will always be 2, and the other side is just e to the power rate times time. So again, that's irrelevant of the initial population. So in order to solve this, we'll take natural log of both sides. The other side just leaves you with the power. So t equals ln of 2 over 0.117, which is something that I can plug into my calculator. So almost 6 days, 5.96 days or so. Actually, this relationship was always going to be true. So we just need to memorize. In order for us to find the doubling time, I just have to take natural log of 2 and divide it by whatever the rate was. So I don't have to solve this equation every time. It's always going to come out to be the same. Right? I mean, I can make the general argument. Okay, I'll make general argument a little later. Well, on this page. So for the doubling time, if this is what I start with, and let's use the capital T for doubling time. That's what your book uses. The other side is 2 times the initial population. So when you divide by whatever your initial population is, you arrive at this equation. 2 equals e to the power k times t. And then you solve it in the same manner, just like above. You'll get t equals ln of 2 over k. It's always going to be the same. So if you know the rate, you can find the doubling time. If you know the doubling time, then you can find the rate really easily. You can always say, well, the rate equals natural log of 2 over the doubling time. So these two will be the same, kind of same formulas. And it's always going to hold true regardless of the initial population. So we're just going to write these two down. These are little quick formulas. So we don't have to solve equations of that type. So doubling time. So either k equals ln of 2 over big T, or big T equals ln of 2 over k. So this is problems from your book, so just we can solve some of them. So here are a list of countries. They either give us the growth rate or the doubling time. Can we fill in the blanks? I mean, if you know one, you know the other right away. For example, for the United States, the doubling time is 70.7 years. So we can find the rate. Rate equals ln of 2 over the doubling time, whatever that is. Okay? So it's roughly probably 1% or so, because ln of 2 is about 0.7. You'll get used to seeing that. After you punch ln of 2 many enough times, you'll keep noticing how that just kind of like almost 0.7. So almost 0.7 divided by almost 70, so it's kind of like 0.001. So yeah, about 1%. So 1% or 0.01. Oh, we can do, what is that? Is that India? We know the rate for India. Find the doubling time for the population of India. So doubling time will be natural log of 2 divided by 0.014. So we'll know how long it takes for the population of India to double. So ln of 2 divided by 0.014. So 49 and a half years, almost. You can round it to 50 or whatever, but 49 and a half years. Okay, so it doubles every 50 years. You go billion in 2 years, it's 2 billion, and did I say in 2 years, and then 50. So 1 billion and 50, it's 2 billion and 50, it's 4 billion, so it's exponential. 4, 8, 16, so it's double. Okay, so it's like the chess game. If you double it at each step, it gets really big. Is that okay? It's pretty straightforward. I have another little table here. This is the money problem, but it's same formula, it's same per or whatever. So let's do the first one. So we know the initial investment, or if I use the new notation, the initial amount, and not equals 35,000, and we know the rate of 3.2. So I can answer the other two questions really fast. They're not related to each other. I don't need to know the doubling time to figure out amount after 5 years. That should be pretty easy. The doubling time is just ln of 2 over 0.032, whatever that is. I can plug that in the calculator. So ln of 2 over 0.032, so 21.66. And the amount of 5 years, so that's again, there's no equation there. I just have to plug everything in. 35,000 e to the power rate times time, which is 5. So that I can just plug into my calculator. Whatever the answer is, it will be that answer. So yeah, play with your calculators. Make sure you're getting the right answers. So 4172 or 4173. So 4172.88. So that was A. So again, that one is really straight up. There's nothing going on. There's no equations. But let's say I can give you B. All I know is the initial amount and the amount after 5 years. Okay? What can I find using these two pieces of information? What can I solve for? The rate. Because there's no way I can find the doubling time at this point without knowing the rate. But I do know it took 5 years to go from 5,000 to 7,130.90 cents or whatever. And that's e to the power rate times 5. Right? So if I put everything that I know, I get that equation. That's an exponential equation. I can solve this. Divide both sides by 5,000. So that cancels. So we have e to the power of 5 times k equals 7130.9 divided by 5,000. So then I'll take natural log of both sides. So it kills the e on the left, leaves you with 5k. On the right, it's a natural log of 7130.9 over 5,000. Is that okay? And then just divide by 5. So that will be the rate. So divide by 5. So I can plug that into my calculator. 7130.9 divided by 5,000. Whatever that is, natural log divided by 5. So 7% or 7.1, whatever you prefer. But when I know the rate, I can find the doubling time. Just go natural log of 2 divided by whatever the answer we just got. Are we okay how we got this answer? So which one am I doing? That one. So 7.1. And for the doubling time, it's just natural log of 2 over 0.0701. So something close to 10 years if I plug it in a calculator. A ln of 2 divided by 0.071. So 9.7, 9.8 years. Is that okay? On your own, see whether you can do, I want you to do D and E, these two. What did you guys get for the rate on D? Anyone? 6.3, because you can just use the doubling time, you don't need anything else. But then having the interest rate, you can rewind time backwards and figure out what you started with. So what did you start with? Did you guys find that? Are you working on it? The first one on D, the amount, the initial amount. So what was the initial amount? Anyone? Yeah, so that sounds right. And the way we set that one up, we know the future amount equals the unknown amount, E, but we now know the rate, and we do know the time, it's 5 years. So that's a linear equation. You just solve for the initial amount by dividing $17,539.32 by e to the power 0.063 times 5, and if you plug it in your calculator correctly, 12.8. Is that okay? These notes are going to be a big mess. I don't know where to write and keep this thing here. So for E, what is the only thing you can possibly find? E is same as B, by the way, as far as the solving it, because that's the same pieces of information. But what can you find? What's the only thing that you can find on E? The rate, right? You know it took 5 years to go from 109 to 136, so you can figure out what the rate was. So what was the rate? 4.5, good. So just like we did B, you set it up. You have 136,503.18 equals 109 e to the power k times 5. Because again, we know it took 5 years to get to that column. So then you solve for it and you get k is 4.5. Knowing that, you can find the doubling time, right? So I'm not going to solve this, we just did that one. So the doubling time then is ln of 2 over 0.045, which is a little over 15 years, 15 years. These notes look fun. They don't make sense. Does that make sense conceptually, though? All right. So, oh yeah, so that's the same set of problem. Yeah, I saved an extra page because we were getting really messy, but I'm done. Okay. So, so that was the growth model. We can also have a decay model. The things decaying, population is decaying, a little pile of uranium is decaying, or whatever. So things that are going down exponentially. So we can have an exponential decay model. And it is the same exact model as the exponential growth. Your book will probably use different letters once again, and I really could not care less about the letters they use. It's all labeled anyways. The only difference between the growth and decay model is that you have a negative exponent. K is still positive. The value for K is still positive, but then we'll put a little negative on top, so that'll make everything to go down. Okay? So just like with the growth model, we have a doubling time. Population of India doubles every 50 years. We can have what we call it a half-life concept. So how long it takes for amount to decrease by half. Okay, so with another group, we started with a full can of surface wipes, and if I tell you the half-life of that is a week, so, and if it has 100 wipes, so how many do I have after a week? 50, and after another week, 25. And after another week, 12 and a half, and then so forth. So it doesn't go to 0 after 2 periods. You keep halving what you left. So you go from a half to a quarter to 1/8 to 1/16. Eventually get something very, very small. But it's the same idea. So the half-life, how long it takes for the initial amount to decrease by a half. And we can derive a formula for that as well, half-life. So let's label that with a T as well, capital T. So again, the concept is the same. if I started with something after t years, I will get 1/2 of that something. So the initial amount decreased by 1/2. So again, it doesn't matter what you start with. When we start solving this equation, when we divide both sides by n naught, it cancels and we'll arrive at 1/2 equals e to the negative kt. So before we had a 2, now we have a 1/2. Now to solve for k, I'll have to take natural log of both sides. So this leaves me with negative kt equals ln of 1/2. So therefore, k or t, doesn't matter, k equals ln of 1/2 over negative t. Algebraically. Is that okay? Now, after all the games you played with logarithms, do you realize that natural log of 1/2 is negative? You do? Now you do. Well, what is the graph of a logarithmic function without thinking all that much of any logarithmic function? What is the graph? Oh, that's the exponential. So like that, right? Always has that intercept. So if the insides are less than 1, you're looking at the negative values for the logs. So every time any log of less than 1 is negative. So since the numerator is negative and the denominator is negative, so the value of k still comes out positive as expected. But so I can improve from this formula. Do you agree with me that 1/2 is same as 2 raised to the power negative 1, just by rules of exponents? And by the rules of logarithms, what can I do with a little exponent if it's inside the logarithm? Multiply, right? The negative, the little power will fall down. So this is negative natural log of 2 over negative t. Negatives cancel. So we still have the same exact formula as we had for the doubling time. It's still ln of 2 over t, or t equals ln of 2 over k. So that's kind of nice. Same formulas to remember. So the only difference between the growth and decay model is just the positive or negative exponent. That's it. The rest will just be the same. So it's a natural log of 2 divided by whatever it is you're dealing with, whether it's a rate or the half-life. Okay? Oh, I didn't erase this part. Well, let's erase this. So here's a table of different radioactive substances, and we either know their decay rate or their half-life. Now, all those little numbers in their names mean really nothing to us. We don't use those numbers. It's just the name of an element. Oops. Keep flipping to that page. So it's kind of like before. Can we fill in the table? If I know the half-life of polonium is 3.1 minutes, then I can find the rate of decay of polonium, right? I can do this really easily. The rate of decay of polonium is natural log of 2 over 3.1. Whatever that is, that's the rate of decay. And it's measured in minutes. It's the rate per minute. Okay? So if I plug it in, whatever that is, I'm sure you can all do that computation. So about 22% per minute. At the same time, I can find the half-life of iodine, for example. The half-life of iodine will be ln of 2 divided by 0.0115, right? ln of 2 divided by rate, which is whatever that is, 60. Now 60 what? What is the units of measure for the half-life of iodine? Days. Right? And so forth. Okay, nice and fun. Let's do some carbon dating. Yeah, here we go. That's a good problem. How many of you are familiar with the process of carbon dating? What was the concept there? Oh, maybe, I don't know. Does anybody, was it explained to you exactly what's happening? Because then I'm just going to make up a story that's probably not true. Well, no, they definitely measure something by burning something, but I think and I'm sure your book goes into the details, but there are two types of carbons in us, 14 and 12, I don't know, probably. And the ratio between them is a constant in a living body, whether it's a tree or whatever. But when things cease to be alive, I believe the amount of carbon-14 drops while carbon-12 remains the same. And then they just look at the change in the ratio, so they'll know by what percentage it changed. So these guys tell us the percentage of carbon-14 went down by 77.2. So we lost 77.2% of carbon-14. Now, we need to know the half-life of carbon-14, and the book tells you that at some point, and you don't need to have it memorized, but it's 5,500, 5,000, whatever that number is, that years, okay, 5750. That's the half-life of carbon-14. So we just need to set up the equation to figure out how old those little bones were, okay? So when you do the carbon dating, what is your initial amount of carbon? Well, no, that's the name of the carbon. So that 14, we don't care. That has no numerical meaning to us. It's a name. It's like a carbon Steve versus carbon John. 14 is the name of the carbon. Okay? So what is the initial amount of carbon when that thing was still running around and playing in the field? 100%. So you start with 100% of carbon, and it went down to what? So it went down by that much. So how much is left? If that's the change in carbon. So 22.8. So we started with 100% of carbon, and we got down to 22.8% of carbon, and K times T, right? The question is how long it took to go from 100% to 22.8%. So we have kind of two unknowns. We don't know the rate, but we can easily find the rate because we know the half-life, right? So K equals ln of 2 divided by 5750. Okay? So I'm just going to stick with that number. I'm just going to carry ln of 2 over 5750, and I'll plug it in the calculator at the very end, because this is a small number, and I have to be very careful when rounding things, because I can, could be a couple hundred years difference when things are this small. Okay, so this is where we're at. 0.228 equals e to the power ln of 2 over 5750 times t. So I use that value for k. And of course I'm lying. Should be a negative in there and a negative in there. Right? It's a decay model. So we've got to have negatives. So take natural log of both sides. We have ln of 0.228 equals negative ln of 2 over 5750 times t. So I can solve for t multiplying by the reciprocal. So t will equal to negative 5750 natural logs of 0.228 over natural log of 2. I'll plug that in the calculator, I'll get some kind of a number. I think we did with the other class, it's 12,246 years, or something close to that. Is that right? Am I remembering things correctly? So that's the idea. So the trick here, you realize you start with 100%, and then you do to whatever percentage you have left. So it's not something measured in grams, but in a proportion. Okay? So that's carbon dating. And how they measure that, they do some burning and counting and things like that. When things get really old, carbon dating does not work. They go for things that take longer to decay. Yeah. That's all there is to it. It's a little probably more complicated at times, but all right. So basically, whatever we just did, using the exponential growth, exponential decay model, all nice, fun, and games. But there are some other exponential models out there. This is called a logistic model. We don't need to know what it is. Usually, it's given to you. So I'm going to do a few problems where the model is just presented to you. We just have to come up and be able to solve equations. So that's an epidemic model. So that's the population that is infected at time t. This is the population of town. And I assume 0.6 is some sort of a rate. 19.9 could be something else. How they come up with those numbers, we don't need to know. They probably did some burning and counting. Yeah. Now, again, we have to graph a function. One thing we can predict that it does have some kind of a y-intercept with t equals 0, and it will grow. That's what you assume. When disease spreads, the number of people that are infected is growing, but what is the absolute highest number that can get infected in that town? 3,500, right? So eventually this function should plateau at 3,500, have a sort of horizontal asymptote at 3,500. And that actually will happen as t is growing because of the negative exponent. This whole expression will approach 0 as t gets bigger and bigger and bigger, because you're putting things in the denominator. So you'll be basically left with 3,500 over 1, which is 3,500. So if I graph this thing on the foo plot thingy, and again I have to be very careful with my viewing window, but it's 3,500 divided by 1 plus 19.9 times e to the power negative 0.6x, close, close. Okay. Okay, it didn't do what well, maybe it did do. Yeah, it did do what I wanted to do. So it has some kind of an x-intercept somewhere here. I'm sorry, y-intercept. But then it keeps growing pretty steadily. And as we get close to 30, okay, I can get close to 3,500 by zooming out. I mean, where is it? Here we go. So it's basically, I mean, it's a little curvier than we think, but it starts evening out and boom, 3,500. So that's somewhere around 20 days. Right? Now, it doesn't quite get to 3,500. 3,500 is an asymptote, and that's just the model. Now, realistically, yeah, you're going to get everybody infected. That's the idea, right? It's not going to be some little fraction of a person not infected. So, how many were infected initially? So all I have to do is to compute n of 0. So that is 3,500 divided by 1 plus 19.9 e to the power 0. So that's 3,500 divided by, it's 19.9 plus 1, so it's 20.9. So whatever that is, this is the initial amount of people infected. And again, remember, these are models, so you're going to get decimals that not necessarily make a whole lot of sense, but this is the best way we can predict of what's happening. So about 167, and that's what we saw on that graph, where the intercept was. It was somewhere around there in that region. So that's what we start with. So then we can find the number of infected after 2, 5, 8, 12, 16 days. So we just have to do, plug in n of 8. You just compute that straight up. 1 plus 19.9 e to the negative 0.6 times 8. You plug that in a calculator, it will tell you how many people are expected to be infected after 8 days. So if I do that, 0.6 negative times 8 equals that. That's the power times 19.9 equals that, plus 1 equals that, in the denominator times 3,500. So here we go. So after 8 days, 3,007. But anyways, when you're given a problem like that, it's all about your ability to manipulate these expressions, because the model is given to you. So you just have to know what to solve for. And we're not really solving for anything, we're just plugging in numbers. So what is the answer to D? Right. So if you're using the model suggests, yeah, you're always going to have 1/1000th of a person away from the full infection. So yeah, the model will suggest no, but realistically, again, that's just the model. It makes a prediction. So, okay. Let's do a cooling problem. So again, here's a model that is presented to you. So if I decide to do something like this on the test, I'll give you that. You don't need to have those memorized. And here's the description of what's going on. So the Newton's law of cooling. Suppose that a body with a temperature T1, so that's something, is put in a surroundings with a temperature T0. So T0 is the temperature around, and T1 is the temperature of an item. Okay? So at some point, the assumption is the temperatures will try to even out. So the example tells you how you take a cup of coffee into a freezer, so eventually the temperatures will balance, right? Hopefully. Actually, that's an unrealistic scenario, but right, the coffee cannot be at 0 degrees. When it freezes, it just stays like that, right? You cannot make ice colder. Is that right? Ice has a constant temperature. But that's right, right? If you get stranded in the woods and it's 40 below, you dig yourself in the snowbank. Because then, your surroundings are about 32 degrees or so, much better than hang out outside. True story. That's how I don't know how helpful that is, but you'll stay warmer. But anyway, so T1 is, in this case, is 105. That's what the item that we're holding. That's the temperature of a cup. And 0 is the temperature of the surroundings. So if I use this model, it's T of T. Well, that's interesting. So that's 0 plus 105 minus 0 e to the negative kt. Okay? So what we know is that in those surroundings, after 5 minutes, the temperature went from 105 to 70 degrees, just in 5 minutes. So that's the value. So T of 5 equals 70 degrees. So if I set things up, it is 70 equals basically 105 e to the negative k times 5. That's what they gave me, right? This is the given thing. Well, the question is how long it takes, well, what the temperature will be after 10 minutes. So in order for me to answer that question, I need to know the rate. Well, I can solve for k. I'll know the rate by solving this equation. All right? If I solve this equation, I only have one unknown. So I can go ahead and find the rate. So divide both sides by 105. Actually, 70 over 105 is just 2/3 equals e to the negative 5k. Take natural log of both sides, and we'll get ln of 2/3 equals negative 5k. So k equals ln of 2/3 over negative 5. Is that right? What is that rate? Somebody compute that? 0.081? Okay. So knowing that, I can figure out the temperature after 10 minutes. Okay? There are actually two ways to do that. I can either say, I'll start at 105 and compute temperature 10 minutes from now, or I can start at 70 and compute temperature 5 minutes from now. Because it took 5 minutes to go from 105 to 70, and it will take another 5 minutes to go from 70 to whatever we do have in the end. If I do both ways, I'll end up with the same exact answer. Does that make sense? Because it's all the same curve. I'm just looking at two different points on the curve. I mean, two starting points on the curve. I still should end up at the same value. So anyways, 10 minutes. All I have to do is to compute t of 10, which is 105 e to the negative 0.081 times 10. Right? Plug that in your calculator. It's not even an equation. I should be able to solve that. I mean, compute that. What did we get? Yeah, 46.7 degrees, right? Just to prove a point, we don't need to do that, but if I compute T of 5, but starting with 70 degrees and doing that for 5 minutes, if you plug that in the calculator, you're also going to get 46.7. Won't be exactly the same because we rounded for the rate, but it'll be close enough, right? If you plug that in the calculator, you get the same answer. So it doesn't matter what you start with. You're still on the same curve. Any questions on this? This is actually a pretty friendly section. It's really just one model, exponential PERT formula for most of the problems. On the rest of them, usually given the formula, I won't be making you memorize any of those cooling or heating or whatever formulas. And you just need to know how to manipulate things and plug them in your calculator properly. Good. So this is our chapter 5.